lunar regolith DEM modeling. And so this is the laser and the pointer.
Okay, thank you. So this is this little work, joint work with University of Alaska Fairbanks and Applied Physics Lab, Johns Hopkins University. And this is sort of initial part of the work that we're doing to make the modeling of the volatile transport in solar, the transport in lunar regolith. As you heard from, for example, Larry Taylor's talk, how solar wind is important at for the studying the processes of the volatiles transport in lunar regolith. So we try to study this process, and what we do here is, as an initial step, we're trying to figure out how deep into the regolith the solar wind particles can be actually implanted. And when so when you consider like the grain of the regolith, so when the protons actually hit the grain, it may damage the lattice and then initiate the whole chain of the collision cascade, and then leave the grain. It may also connect. It may actually diffuse out of the surface on its own, or connect to other hydrogen or oxygen molecule, and then leave it as a whole molecule from the surface. So it can actually stick inside the grain. But to figure out what actually grains are affected, we try to simulate it with DEM. DEM is a discrete element method model, and the whole process is a discrete. It's not a continuous. So that's why we want to actually use some model that represent each grain individually, each particle in a granular material. So it also, the discrete element method provides a good representation for the regolith. It was tested on different tasks before. We did a lot of simulations, for example, for geotechnical tasks on Mars. For the Mars exploration rover wheel, there was a recent publication in Journal of Thermomechanics. And then for the ARM mission, for the boulder retrieval from the surface. So it's a well-tested model. It also allows to simulate different groups of particles with different behavior, and it actually can mix polyhedral particles together with spheres, which is very handy for this particular task. So this first task is pretty much the ray tracing task. So we're trying to figure out how deep protons can actually go through the little holes that that exist between the grains. And the first task was to make the actually regolith model. So for that we use some sort of is it working? Okay. So we use different. Let me get back. We use the CT scans of GRC3 simulants from GRC. We did it at University of Alaska, and then created the particles and packed them, just dropping them using gravitational deposition process to create the regolith itself. The challenge here is to create actually high porous material. It's not that obvious how to do it initially, but when you to do that, we actually use initially artificial mechanical properties for the contact mechanics here, like changing friction between the particles, adjusting cohesion. So we actually were able to build different particle beds for different porosities, and we expect the high porosity on the top surface. Another challenge was to actually create pretty even surface, and for that we use different sieves also to produce that. The next step was actually implantation simulation, and we generate like many protons, little particles, spherical particles, actually the size of the protons. Here they increased just for visualization. And randomly, in a random position within some square on top of the regoliths, and then assign the constant velocity to each of them, and then we can see how they actually distributed into the regoliths. And you can see they can go pretty deep there. They stop moving at the moment when they touch a grain. So at this moment they stopped here. So again, they generated just on about half of the whole particle bed. So we don't want, when we change the incidence angle, we don't want the particles to miss actually. So to calculate the vertical distribution, it's pretty straightforward. We just divide the vertical direction into the segments, count the number of particles that get into the segments, obviously, and then divide it by the total number of particles and the size of the segment, then you produce the differential distribution. So all together, so we just, again, deposit the particles, generate the protons just above the regolith, set the constant velocity, shoot them, and then compute the vertical distribution in terms of the, so we calculate the distance in terms of the equivalent diameter of the particle, so which means that this is the diameter of the sphere that has exactly the same volume as the grain. Another challenge was to determine the surface is not even, so from where we actually calculate the distribution. So we envelope the surface around the regolith to represent the level from which we start calculating the depth. Particle size distribution that we used, we get the JSC1A simulant data from Glenn Research Center. And what we do here is we have the mean value, and then we cannot, obviously we cannot simulate the whole distribution in a DEM. Just imagine that if you have like even 100 times difference between the particle size, it means 1 million difference in the volume. So you need 1 million particles around like one big one. So it's just impossible computationally. So we need to cut sort of a window within the distribution. That's what we do around the mean value of the distribution here in a log scale. And we sort of characterize the window by the ratio of the maximum size to the minimum size. So you have like 2x, 3x, 4x windows and so on. So even for 4x it's pretty challenging already because the volume difference becomes, this is a 64 difference. But what essentially we'd like to do, we'd like to see if we, our results converges at some stage, so we can stop at some window here. So particle size distribution influence, actually a little bit surprising results initially, that when you increase the window size, you're actually able to reach deeper into the regolith. And this is pretty much happens around the large particle that rests on the surface. So the large particles create more holes and opportunities for the protons to actually reach deeper. And what we also found that we pretty much can stop at 4x, maybe 5x window, then when all the distributions become pretty closed. The packing density influence, there are no surprise that with a lower packing density, like opposite from porosity thing, that we can reach actually much deeper layers. And so we can reach like 7/8 layer. It's when you see here as a particle, it's pretty much a single particle detected, 1 out of 50,000 here. Okay, yeah, I'm pretty close. And then another, what we checked is the incidence angle influence. Obviously, with increasing the incidence angle, if you calculate it from the normal to the surface, the penetration depth for the protons decreases, but it still reaches pretty deep for high porosity. And the last thing that we've done is essentially we try to analytically understand how protons should be distributed after they deposited like this. And if we try to figure out if each time when you have the set of the protons that go through the regolith, if you think that it's sort of a poison process when there is always an equal probability for the proton to hit a grain, then it should be something that like a gamma distribution. So we try to feed a gamma distribution into the final rate, which would reduce the parameter space just to 3 parameters, much easier to analyze and use as a boundary condition for future transport model. Then, and indeed, the gamma distribution fits pretty well here, as you can see. So, as a conclusion here, we use the discrete element method to compute the implantation rate for different layers of lunar regolith, and as the process is pretty discrete, that pretty natural choice here. We found that the penetration depths of protons strongly depend on porosity, and we can get 1 out of 100,000 protons reach level 7 and 8. We have wide particle size distribution provide deeper penetration of protons around large particles, and we also were able to find a pretty good function that fits the final implantation rate. So that's it.
We have time for 1 or 2 questions.
Hey, Regolith ATL. So obviously, I think this is useful work. You're working with us already. What's the next step for using this? Because you developed the ability to have protons implant into the surface. So where do we go from here with this work?
So the next step, so we have now the boundary condition pretty much for the next transport model. And then from here, as if, so we will try to simulate in DM how the, what the next stage, what the protons doing afterwards, how they, for example, move around along the grain, how they jump from one grain to another, to actually to find the rates for the continuous model. So it's on a micro scale, how actually the protons migrate on a larger scale already. So as a feed for macro models like that use a continuum approach.